Okay, in this video we're going to talk a little bit more about Lenz's law and Faraday's law. If you recall in the last video I told you how a changing magnetic flux can induce an EMF or an electric current in a loop of wire. And Faraday's law tells us the magnitude of that induced EMF. So the EMF here is equal to the rate of change in the magnetic flux times the number of coils in the loop. Remember that magnetic flux is equal to the amount of magnetic field passing through an area. And only the perpendicular component of the magnetic field is relevant here. So the faster the magnetic field or the area is changing, the greater the induced EMF. Now this negative sign, if you recall, I said is Lenz's law. It tells us that the induced magnetic flux creates an opposite magnetic field. So Lenz's law states the induced current will be in a direction that creates a magnetic flux in the opposite direction to the original flux. Okay? This is something that you basically should just memorize. One of the few things in physics that you need to memorize, and it's Lenz's law. Quite often you might be asked on a question to justify the direction of the current, and you could say it's because the induced current, according to Lenz's law, the induced current will be in a direction that creates a magnetic flux in the opposite direction to the original flux. So how do we actually apply this? Well, if you recall in the last video, we already worked out the solution to this problem. We have a coil and a magnetic field that's directed into the page. It's 0.60 Teslas into the page, and it changes to 0.10 Teslas out of the page. And we know that the EMF here, when we worked it out with Faraday's law, was 0.14 volts. But the current that gets created in this loop of wire as it goes around can either be going clockwise like this, right? Or it can be going counterclockwise. So there's two different possibilities here. Which way is the current going, clockwise or counterclockwise? And that's what we're trying to use Lenz's law to determine. Okay? So the first thing we want to do is, because it depends on the original change in the magnetic flux, is write down the direction of that change. So the first thing I'm going to say is that the magnetic flux starts off going into the page, and it changes direction to out of the page. Okay? And it's decreasing. So it goes from 0.60 Teslas to 0.10 Teslas. So there is a decreasing magnetic flux into the page. The other way we could look at it is that there's an increasing magnetic flux out of the page. Right? It's going from a direction into the page, and we're increasing the amount of magnetic field coming out of the page. So either way, we can write this as a decreasing flux into the page or an increasing flux out of the page. Then the next thing we would write down would be our Lenz's law. I'm not going to write it out. Hopefully you can just copy it down from the previous slide. So Lenz's law basically says that the current will generate a magnetic flux opposite to this. So either opposite to a decreasing flux into the page or opposite to an increasing flux out of the page. So what would be the opposite of that? Well, if I'm decreasing the flux into the page, the opposite would be to increase the flux into the page. Or if I have an increasing flux out of the page, I can have an increasing flux into the page, right? The other opposite of this would be a decreasing flux out of the page. So notice that what I've done is basically written down the opposite. So if it's a decreasing flux into the page, I have an increasing flux into the page. If I have an increasing flux out of the page, a decreasing flux out of the page. So I basically am writing down the opposite of this. So now that I know what the magnetic flux is going to be doing, I need to determine what type of current will create this. Now it's hard to determine a decreasing flux out of the page. So I always try to eliminate anything that is decreasing and just deal with increasing. So if I have a decreasing flux into the page, the opposite must be an increasing flux into the page. So the current will generate a magnetic field. Remember our first right-hand rule. So this wire, inside the loop of wire, I want an increasing flux into the page. So I want my fingers inside the loop of wire to be pointing into the page. If they're pointing into the page, my thumb, when I grab the wire, is going in a clockwise direction. So the last thing I write down here is that a clockwise current creates an increasing flux into the page. So I've now determined the magnitude of the EMF and the direction of the current. So the current has to be going clockwise to increase the magnetic field going into the page. So remember again, if I want to create more magnetic field going into the page, I need a magnetic field going in this direction. So coming out of the page on this side, into the page on the other side, and I've used my right-hand rule to determine the direction of that that electric current. It's very complicated, I'll admit, but the good news is that it's usually a 50-50 situation. It's either going to be going clockwise or counterclockwise or to the left or to the right or up or down or whatnot. So as long as you know Lenz's law and can write it down, and as long as you can determine what's happening originally, hopefully you can determine the change in the magnetic flux afterwards and use your right-hand rule to determine the direction of the current. There's a really good example question in the textbook. It's example number 21-2. It has about 5 or 6 different examples. I suggest you work through those. And because it's an example question, it has the full solution written out. So try to work through those. And as always, if you have questions, come and ask me in class.